So we're going to be looking at systems of equations. So right now we're going to deal with systems of linear equations, but later on we'll deal with all different types of equations and systems of equations. So a system of equations are equations, well, you have multiple equations, two or more equations. Each equation has at least one variable, and we're trying to solve for the solution. And the solution has to satisfy all of the equations in the system. So you've probably worked with systems of linear equations before and have looked at using the substitution method and or the elimination method to help you solve these systems. I'm going to teach you a different way to do it using matrices to help you solve. And it's a way that you're pretty much doing the same thing you would be doing when you were solving it before, but it just keeps it a little more organized and easier to follow through. So let me share my screen with you. So when we're looking at systems of equations with two equations, two variables, usually x and y, but it could be a different variable, let me show you what's going on graphically. So if we have two systems or two equations, there's three things that could be happening if we have two equations. So we're looking at linear equations. So we have lines when we're graphing these. And so there's three possibilities too when we're solving these systems. We can have what is called an independent system. And so there's only one solution to the system. And so what's happening graphically, if there's just one solution, is that your graphs are intersecting in one spot. So here's an example of what something might look like. And so that spot where they're intersecting is your solution. You could have a system where you have no solutions. And so if you have no solutions, what's happening is when you graph those two lines, you have parallel lines. So we might have a line that looks like this and a line that looks like this. So they would be parallel lines, but so parallel lines, recall, have the same slope. They just can't have the same y-intercept. So same slope, but different y-intercepts. The other case that you could have is where you would have an infinite number of solutions. And so what's happening graphically there are basically, and you might not notice that at first when you're looking at your lines, but they're exactly the same line. And so the line is going to be lying on top of each other. And so every point that lies on those lines is a solution to that system. And so this is a case where we have an infinite number of solutions. So if you looked at the equation of lines again, you would notice that they would have the same slope, but in this case, they would also have the same y-intercept. So that's what's going on graphically if we're looking at two equations, two unknowns. If we're looking at equations that have three variables, three unknowns, then we get into 3D pictures and it's a little harder to graph. So let me just pull up some images of what could happen for you. So in front of you are some images of what could be happening if we're looking at three equations and three unknowns. Basically, you have a plane. So think about it as a piece of paper that is going on infinitely in all directions. And so there's three possibilities. Again, you're either going to get one solution, no solutions, or an infinite number of solutions. So you could have, in this first case, it looks like you have 3 different planes, but they're all parallel. And so they're never going to overlap. And so there are no solutions. So in the next piece here, you have an example where you have 2 planes that are parallel and then 1 plane that is intersecting those 2 planes. And again, in order to be a solution to the system, you have to have the point has to satisfy, or points have to satisfy all of the equations. So in that case, they're not going to be satisfying all those equations. So there's more examples of no solutions. And then you have an example down on the bottom row, left-hand corner, where you would have 1 solution. And so that it would be the 1 spot where they all 3 intersect. And then there are cases where you would have infinite number of solutions. So in this case, where you have those 3 equations, 3 unknowns, they're all overlapping at this line. And so that line, any point that's on that line, is going to be solutions to that system. Or you might have those 3 planes that are lying on top of each other. So any points on the plane would be solution. And again, here's another example where you have an infinite number of solutions, 2 coincide planes, and an intersection is the line. Okay, so let's look at what I'm hoping that you guys would know by the time that I finish lecturing on this information. So we are going to be using what I said is called matrices to help us solve these. So you should be able to take your equations and you should be able to rewrite it and put it into a matrix. And we call this matrix an augmented matrix. So you should be able to write an augmented matrix of a system of linear equations. You should be able to write a system of equations from the augmented matrix. So given the matrix, you should be able to write those equations down. You should be able to perform row operations on your matrix. Matrix is just singular for the word matrices, and I'll define matrix in a second. And solve systems of linear equations using these matrices. So a matrix, we have a matrix in front of us here. So a matrix is just defined as a rectangular array of numbers. And so you have your rows. So rows are horizontal. So that would be our row 1, our row 2, so the horizontal line, etc. And then we have our columns. So columns are our vertical rows. And so our columns here, oops, thicker, are in here. Okay, so our columns are our vertical array of numbers. So each number in the matrix we call is an entry. And so notice that when we wrote this out, or this matrix has these subscripts, and there's 2 numbers on those subscripts. Those subscripts actually help us locate which number we're talking about. And so the subscript helps us locate which row. It always goes first row and then column. So for example, if you saw A and then sub 2, usually a comma 4, this is going to indicate that we're looking at the 2nd row, 4th column. So the entry. In the 2nd row and 4th column. So in front of us, we have a couple of systems of equations. Part A, we have a system of equations with 2 variables and 2 equations. The first equation is 3x minus 2y equals 3. And the second equation is negative 2x plus 1 equals negative 2. So when we're writing an augmented matrix, all we're writing are the coefficients and the constant of the matrix, of the system of equations. So we want to make sure that all of our x variables are lined up, all the y variables are lined up. And so what we're just doing is it's either like a huge parentheses or huge brackets, depending on how you want to do it. But this first equation is going to be the first row of my matrix. And so the coefficient is 3. The next coefficient is negative 2. And then the goes equal. So usually between the terms with a variable and the equal sign with a constant on the other side, you see this vertical line, meaning this is an augmented matrix. And then on the other side of that vertical line is a 3. So that is our first row of our matrix. Our second row of the matrix is going to be negative 2. Coefficient in front of y is 1. And then on the other side of that vertical line is negative 2. So the first column represents the x coefficients in front of our x variables. And the second column is our y. And this is equal to some number. So you should be able to do that. In the next example, we have 3 equations, 3 unknowns. So we're just rewriting this as an augmented matrix. And so I want to make sure that all my terms are lined up. So actually, I want to rewrite this. So let's get the constants on the other side. I noticed that I have x, y, and z's in my equations. So let's first rewrite this before we write the augmented matrix. And so I'm going to subtract 5 on both sides of that first equation. And so if I did so, I would have 3x minus 2y. I notice there's no term with z in here. So we can just put a placeholder if we want, plus 0z is equal to negative 5. So my second equation, let's rewrite that. Let's get the constant on the other side of our equal sign. And I notice that there's no term with y in here. So let's put a placeholder, 0y, underneath the place where the other y term is for the first equation. So rewriting that second equation, we have negative 2x plus 0y plus 4z. And then let's subtract 2 on both sides of our equation. So this is equal to negative 2. And the third equation, we have, that's already how we want it, x plus 4y minus 7z equals 0. So it's in the form that I could write my augmented matrix. So my first row is going to be 3, negative 2, 0, vertical line where the equal sign is, and then negative 5. Second row is going to be negative 2, 0, 4. On the other side of the vertical line, negative 2. And the third row is going to be 1, 4, negative 7, and then 0. So this matrix is just a way to reorganize our equations. It's just that we're using those coefficients and constants instead of having those variables in there. So we should be able to go the opposite direction. So given a matrix, we should be able to write the equations that is associated with that matrix. So for instance, if we were given the matrix here, first row is negative 2, then 1, and then the vertical line 3, and the second row is 1, 1, and then on the other side of the vertical line, negative 2. So notice in this example, this has brackets instead of parentheses. You can do it whatever one that you prefer. So looking at this, we're thinking of the first column are our coefficients of our x terms. The second column is the coefficient of our y terms and then equals some number. So writing out our equation, we have negative 2x plus y is equal to 3. Our second equation, we have 1x, don't have to write the 1, plus 1y, so plus y is equal to negative 2. So this is the equations that are associated with that augmented matrix. So let's look at one more. And so we have a matrix here. This has 3 rows. Notice there's 4 columns. Let's think of the first column as our x variables. Second is our y. Third is our z. And then we have our equal sign, some number. So rewriting that system, we have 3x minus 2y plus 5z is equal to 3. So our second equation here is negative 2x plus y plus 4z equals negative 2. And then the last equation is x plus 4y minus 7z is equal to 1. Okay, so now that we know how to rewrite systems of equations as augmented matrix, an augmented matrix and vice versa, let's look at properties that we can do to help us solve these systems of equations. So in front of us, we have row operations that we can do to our matrix. And while we're doing these row operations, we'll be changing our system of equations, but we'll be keeping equivalent solutions to both. And so what we can do is we can interchange any 2 rows. So we can swap rows. So I can make my row 1, my row 2, and my row 2, my row 1, for instance. We can replace a row by a constant non-zero multiple of that row. So basically we can take a whole row and multiply it by a non-zero number. It just can't be 0. So any number that's not 0, and then replace it. Or we can replace a row by the sum of that row and a constant non-zero multiple of another row. So let's look at an example of the following. So we have an example where we have a 2 by 3 matrix, 2 rows, 3 columns. Our first row of that matrix is 1, negative 2. Then we have that vertical line, then 2 on the right-hand side of that vertical line. Then the second row, we have 3, negative 5, 9. So what is it meant by R sub 2? And it's asking us to apply the row operation. R sub 2 is equal to negative 3 row 1 plus row 2. So R sub 2, the way they're using their notation is this is going to be our new row 2. And we're going to get that new row 2 by looking at negative 3 times the first row. And then we're going to sum this with row 2, that little R sub 2. So let's do that. And so we're only changing row 2 here. We're using row 1 to manipulate row 2, but we're only changing row 2. So usually what I do is I will write down the row that I'm not changing. And so our row 1's going to stay the same. It's 1, negative 2, vertical line, 2. So we can do a lot of this work in our head. So we're looking at -3 times this row 1. And then we're going to sum it with a number below it plus row 2. So if I look at -3 times 1, that's -3 plus the number right below it, which is 3. So -3 plus 3, that would give me 0 here. And then I'm going to go to the next entry in that row. So I'm looking now at -2. So I'm telling me to multiply -2 by -3. So -2 times -3 is 6. And then we're summing it to the entry below, -5. So 6 plus -5 gives us 1. So now we're going to the next entry in our first row, our constant 2. We're multiplying that by -3, and then we're summing it to our 9. So 2 times -3 is -6, and -6 plus that 9 gives us 3. So we're just manipulated that second row by changing it with a multiple of one row and summing it with the other row. So let's go back here and let's read off what this matrix says. Let's rewrite this as an equation or equations. So the first row is x minus 2y is equal to 2. The second row here is 0x plus 1y. So I'm just going to write y is equal to 3. So from this point, we could solve for this system of equations. We know what y is, so we can use our substitution. So I have y is equal to 3. So we can go back into our other equation and replace y with 3, and then we would have an equation with just one variable in there. And so doing that, we would have x minus 2 times y, but y is 3, is equal to 2. I want to change colors, so we'll not change colors in a second. So we have x, and then we have -2 times 3, so -6 is equal to 2. We can solve for x by adding 6 to both sides, and so we get x is equal to 8. So our solution to the system, x is 8 and y is 3. So you should be able to go back up into that system of equations and solve for that. So let's rewrite that system of equations that we were given in the augmented matrix. And so this is going to be here, x minus 2y equals 2. Second row tells me it's 3x minus 5y equals 9. And then let's go back and let's check this. So we found that x was equal to 8 and y was equal to 3. So let's go back into this system of equation and show that our solution is correct. And so for the first equation, we need to show that that's a true statement when x is 8 and y is 3. So we have x, so we're going to replace that with 8, minus 2. We see a y, so we're going to replace that y with 3. Is that really equal to 2? Yeah, we have 8 minus 2 times 3 is 6, and 8 minus 6 is equal to 2. So we just showed that 8, 3 is a solution to that equation, but it also has to work for the other equation in the system. And so we have 3 parentheses. Let's plug in 8 inside that parentheses, minus 5 times y. So we're going to put parentheses where the y is and replace that with 3. Is this equal to 9? So 3 times 8 gives us 24, minus 5 times 3, which is 15. Is this equal to 9? 24 minus 15 is 9, and 9 equals 9. So you can always go back and check to see if your work, what you did for your work, was correct. It's easy to make minor errors in solving these, and so checking could be really helpful. So we have another example in front of us now. It says find a row operation that will result in the augmented matrix where we are having 0 in row 2 and column 1. So looking at our matrix, our first row of that matrix is 1, then 2, then 3, the vertical line, -7. Our second row is 2, 5, -1, then 0. Our third row is -3, 6, 2, and -5. So it wants us to look at the operation that we would need to do to make row 2, column 1, which is this 2 here, a 0. So we will see in a minute that that first row, first column, we usually want a 1 there. There's already a 1 where we want it. And we're going to use that row, that's where we want that 1, to manipulate the entries above and below it. In this case, there's no entries above that 1. So we want to manipulate this matrix so that 2 is now a 0. And so I'm going to use that first row to manipulate it. And I know that -2 plus 2 is 0. So if I look at -2, so I'm going to have my new row 2 equal, I'm going to take -2 times my row 1, and then I'm going to sum it to my row 2. So I'm really keeping row 1 the same. I'm just using it to manipulate row 2. So I'm going to rewrite row 1, 1, 2, 3, vertical line, -7. And now we're going to do the operations. So -2 times this row, and then adding it to the next row. So I have -2 times this 1 is -2, plus this 2 here is 0. Going to the first row, second column, I'm looking at this entry -2, multiplying it by this -2. I'm sorry, that's +2. 2 times this -2 is -4, plus the entry below, which is a 5. So I have a -4 plus 5. This is going to give me a 1. So I have -2 times this 3. So that's -6. -6 plus the number below it, -1. -6 plus -1 is -7. Going to the next column. So -2 times -7, that's 14, and then add it to the 0 below. So 14 plus 0 is 14. So let's do the same thing. Part B says, write your result from part A in the space. Well, we already did that. And then find the row operation that will result in the new augmented matrix having 0 in row 3, column 1. So looking at row 3, column 1, which is -3, we want to make this a 0. So I'm going to use this first row to manipulate that. So I'm going to put my directions of what I'm doing. So I'm looking at changing my row 3. So row 3, my new row 3, I'm going to get by looking at, well, 3 times 1 is 3, and then the minus that 3 below will give me that 0 I want. So 3 row 1 plus row 3 is going to give me my new row 3. 3, row 1 plus row 3. So 3 times 1 is 3, plus a negative 3 gives me 0. Move to the next entry in the first row. So 3 times 2 is 6. 6 plus 6 below gives us 12. Next column, we have 3 times 3 is 9, and 9 plus this 2 is 11. Going to the next column, 3 times this negative 7, that's negative 21, and negative 21 plus this negative 5 is negative 26. So we have our new augmented matrix, and we've manipulated it and got zeros in the entries below that leading one. So we've been using these row operations, and we're trying to manipulate our matrix to look like the following form. So there's what is called row echelon form, and there's what really I like to prefer to do is reduced row echelon form. Well, what does it mean when the matrix is in row echelon form? So to be in row echelon form, the entry in row 1 and column 1 is a 1. And then below that 1, zeros appear below it. Okay, so we just manipulated that matrix to look like that. We had entry in row 1, column 1, a 1, and we manipulated it and got zeros below that, what is called a leading one. So the other thing that needs to hold is the first non-zero entry in each row after the first row is also a 1. And then zeros appear below it, and it appears to the right of the first non-zero entry in any row above. Any row that contains all zeros to the left of the vertical bar appear at the bottom of our row. Okay, so row reduced echelon form, basically, we want it to be in row reduced or row echelon form. That leading entry in each non-zero row is a 1. We call it the leading 1. And each column containing a leading 1 has zeros in all the entries above that leading 1. So we want that leading 1, we want zeros above and zeros below in that column. Okay, so we're gonna now look at the system of equation. We're gonna use matrices to solve this system. So our first equation is x plus y minus z equals -1. Our second equation is 4x minus 3y plus 2z equals 16. Our third equation is 2x minus 2y minus 3z equals 5. So just some tips for you. When you're writing out your matrix, well, when you're writing out your problem, just make sure that you've copied it down correctly. So that's one of the errors I see is not copying it down correctly. So just double check that, because it's a lot of work to find your errors if you made an error. So let's look at this, and I'll give you some more tips as we are going through and solving this. So our first row, and I'm making sure all my x terms are lined up, which they are, y terms, which they are, z terms, and then the constant on the other side. So our first row of this augmented matrix is 1, 1, -1. Put your vertical line, and then -1. Our second row is 4, -3, 2, 16. Our third row is 2, -2, -3, and 5. Our goal, if it's possible, it's not always possible, is to get our matrix to look like the following. So in this case, 1, 0, 0, and some number, let's just call it A. 0, 1, 0, and some number, let's just call it B. And then 0, 0, 1, and let's just call this C. So if we can manipulate our matrix to look like the following, it would give us our equation, because our first column is our x value. We would see that x plus 0y plus 0y is equal to, 0z is equal to A. Our second column was our y values. And so we have 0x plus 1y plus 0z is equal to B. And the third row gives us 0x plus 0y, third column is z, plus 1z, so z is equal to C. So our goal, again, is to get these ones in this main diagonal and zeros above and below those ones. When we're doing this, it's really important that we go from column to column. So working with column 1, we're going to manipulate it to look like what we have above. Then when I'm done with that, then I'm going to work with column 2. Once I get column 2 to look like what I want it, then I move to column 3. Usually the first goal when I'm getting into that column is to get that 1 where I want it. And so if there's not a 1 where I want it, in this case, there is a 1 where I want it. If there was not a 1 where I wanted it, there's 2 things I could do. I could either multiply that row by the reciprocal of that number. That's not a 1 that I want to manipulate to be a 1. Sometimes that's kind of messy because you're going to sometimes deal with fractions. And if we don't have to deal with fractions or decimals, I try to avoid it. Or the other way to make that a 1 is multiplying a different row by a number and summing it to that row. Actually, there's another way to do it. If there was a 1 where in the column below or the row below, I could swap my rows. Okay, but I do have the 1 where I want it. So I'm going to use that 1 to make zeros in the entries below. So I'm going to keep my row 1 the same. So I have 1, 1, -1, vertical line, -1. So to get that 4 to be a 0, I'm going to look at row 2. My new row 2 is going to be -4. Row 1 plus row 2. So -4 times 1 is -4, plus this 4 is a 0. Move into the next column. -4 times 1 is -4, plus -3 is -7. Going to the next column, -4 times -1 is +4. 4 plus this 2 below is 6. Then we have -4 times -1, so that's +4. 4 plus 16 is 20. Okay, so we just manipulated row 2 how we wanted it. And we're going to now go and manipulate that row 3, column 1, that 2 in that entry. We want to make that a 1. So my new row 3, I'm going to get by -2 times this row 1 plus this row 3. So -2 times 1 is -2, plus this 2 below gives me 0. -2 times this +1 is -2. -2 plus -2 is -4. -2 times this 1 up here is +2. 2 plus -3 is -1. I have -2 times this -1, that's +2. 2 plus this 5 is 7. So I've manipulated my matrix to have that leading 1 and then the zeros below it. So I've gotten that first column how I want it. So now I'm going to that second column. So that second column, my goal is to first get that entry in the second row, second column. I want that to be a 2. Right now I have a -7 right there. So I could either multiply through by -1/7, but then I noticed that my other entry, 6 and 27, doesn't go in there evenly. I cannot use the 1 in the row above, because if I use that would get me a number where I just made a 0 in that row, and I don't want to do that. I do notice, though, that -2 times row 3, that -2 times -4 is +8, and 8 plus that -7 would get me a 1 where I wanted it, and wouldn't get mess up the zeros where I just got them. So let's look at, I'm wanting to change row 2, but I'm going to keep my row 1 and row 3 the same. So I'm going to just rewrite my row 1, 1, 1, -1, vertical line, -1. And I'm going to rewrite my row 3 down here, 0, -4, -1, and then 7. So I'm manipulating this. I'm manipulating it, and I'm changing my row 2. So my new row 2 I'm getting is equal to, we said, -2 times row 3 plus row 2. So -2 times this 0 is 0, plus the 0 above is also 0. -2 times this -4, that's +8. 8 plus -7 is 1. -2 times this -1 is 2. 2 plus 6 gives me 8. -2 times this 7 is -14. -14 plus this 20 is 6. So we got our leading 1 in row 2. We're going to use that row 2 to multiply it by some non-zero number and add it to the row above to get that to be a 0. So I want that 1 above my leading 1 in row 2 to be 0. So let's look at, we're changing row 1. So it's going to be our new row 1. This is going to be negative row 2 plus row 1. So I'm going to rewrite this. First, I'm going to just put in my row 2 because I'm not changing it. I'm just using it to change my other rows. So my second row is staying the same, 0, 1, 8, 6. Let's look at our new row 1. So I'm looking at negative row 2 plus row 1. So negative times 0 is 0, plus 1 is 1. -1 times 1 is -1, plus the 1 above is 0. -1 times this 8 is -8, plus the -1 above gives me -9. Then I have -1 times 6 is -6. -6 plus -1 is -7. So now we're going to go and we're going to manipulate this. And I just erased that. So that was -2, 14 plus 14. Okay, so no, that entry was a 7 there. Okay, so we're manipulating this. We want to get rid of this -4. We're going to use this row 2 to get rid of that -4. So our new row 3, we can get that by 4 times row 2 plus row 3. So 4 times 0 is 0, 0 plus 0 is 0. 4 times 1 is 4, minus 4 is 0. 4 times 8 is 32. 32 minus 1 is 31. 4 times this 6 is 24. 24 plus that 7 is 31. So when you're working through the homework, they might show examples and they might just stop there and go back and do substitution to solve. Because technically that last row there is 0x plus 0y plus 31z equals 31. So we can easily solve for z there and do back substitution into the equations above. We could write those out to figure out what x and y are. But I'm going to keep going and get it into this goal of what I wanted, this row reduced echelon form. So I finished column 2. So I got everything what I wanted in column 2. So now we're going to move to column 3. So our first goal is to get the 1 where we want it. And so I want to manipulate this so that that 31 is a 1. And so the only way I can do that without screwing up my other columns I just did is I could look at 1 divided by 31 times row 3. And this is going to be my new row 3. So I'm going to rewrite the first row because I'm not manipulating or changing it right now, which is 1, 0, -9, -7. I'm going to rewrite my second row, 0, 1, 8, 6. And I'm going to get my new row 3 by multiplying everything through by 1 over 31. Well, 1 over 31 times 0 is 0. 0 times anything is 0. 1 over 31 times 31 is 1. And 1 over 31 times 31 is 1. So we got the 1 where we want it. We're going to use that row or the 1 where we want it to get rid of the entries above. So now I'm going to be using this row 3, but not changing it. So let's write down row 3, 0, 0, 1, and then 1. Okay, let's get rid of this -9. So row 1, I'm changing. This is equal to, well, 9 times row 3, and then add it to row 1. That would get us the 0 where we wanted it. Well, 9 times this 0, 0, plus 1 is 1. 9 times this 0 is 0, plus 0 is 0. 9 times this 1 is 9, plus -9 is 0. 9 times this 1 is 9, plus -7 is 2. Okay, so we got row 1 as we want it. And now we're going to go to row 2, and we want this 8 to be a 0. I can manipulate that to be a 0 by my new row 2. Let's look at -8 times that row 3. And then if we sum it to row 2, that 8 will go away. So 0 times -8 is 0, plus 0 is 0. 0 times -8 is 0, plus 1 is 1. 1 times -8 is -8, plus 8 is 0. And -8 times this 1 is -8 plus 6, which is -2. So we manipulated this so our solutions fall out. we get in this case that our x value is 2, our y value is -2, and our z value is 1. So to write this as an ordered pair, we write it in the form of x, y, z. So first number is 2, comma, second number, which is -2, and the third number, which is 1. So if we go back in and plug in those values for x, y, and z into each equation, there where we started, that should satisfy all 3 equations. If it doesn't, then we did some arithmetic error somewhere in there, and you need to go and find it. And so this is where it's important that you're writing down the steps that you're doing to get your new rows. And so you can go back and kind of trace your line of thinking and hopefully find the error. These can get really tedious if you get them wrong to grade. So it's kind of nice you guys are watching me. So hopefully if you see me make any errors as I'm going through this, please stop me. And that's for my class that is live right now. So I just wanted you again to be aware that it's nice to get to this point where it's in row reduced echelon form to find the answer, but you can stop while you're doing this process and still find the solution. So this matrix down here on this that I just starred, if I rewrote this as a system of equation, that first row would give me x plus 0y, so I'm not going to write that y, minus 9z is equal to -7. That second row, 0x plus 1y, so y, plus 8z is equal to 6. And that third row, 0x plus 0y plus 31z is equal to 31. And so notice here, we can easily figure out what z is by dividing both sides by 31. And so from here, divide both sides by 31, we get z is equal to 1. And so I can go in and do back substitution into the equation. So if I went up to this equation above, and where I see a z, replace it with 1, I would be left with an equation with just y left in there, and I could solve then for y. And so doing that, we would have y plus 8 times z, but z was 1, so I'm replacing that z with 1, is equal to 6. So let's get y by itself by subtracting 8 on both sides. And so by doing that, I get y is equal to 6 minus 8, which is -2. And so looking now at the third equation, I have an x and a z. So if I go in here and I rewrite and substitute z with 1, I could solve for x. So doing so, I would have x minus 9 times z, but z is 1. This is equal to -7. So getting x by itself, I could add 9 to both sides of my equation. So I would get x is equal to -7 plus 9, which is 2. Which notice is the same values I got by manipulating my matrix to be in that form. So we can stop if you see that, your answers are going to fall out pretty easily. Because you can see what some of the solutions are or what a solution is, and you can see if you go back and do back substitution, things will fall out. I'm okay with you guys stopping there if you would like, and then rewrite it as equations to solve. So the system of equations that we just looked at is an independent system because it has one solution. Another word you might hear is this is a consistent system, meaning it does have a solution, or at least one solution. So if you're working through these matrices to solve your system of equation, and you get a row of all zeros, then that's still true because you get 0x plus 0y plus 0z equals 0. But it is a dependent system, meaning that there's going to be an infinite number of solutions. So row of all zeros, we're going to have a dependent system, which is still called a consistent system. And we'll manipulate it so that we can figure out how to find the solutions to the system. If you're working along with these matrices and you get a row of all zeros except for that last number, then we can stop. There's no solution. It's inconsistent. For instance, if you got 0, 0, 0, and a 1, that's saying 0x plus 0y plus 0z is equal to 1. And that's impossible to do. There's nothing I can plug in for x, y, and z and get back 1. And so we could stop there and say there's no solution. So let's look at a couple more examples of solving these systems of linear equations using matrices. So our next example in front of us, we have this system. We're given that first equation is x minus 3y plus 2z equals 6. The second equation, we have negative 2x plus y minus 3z equals 10. And the third equation, I have x minus 8y plus 3z equals 28. So first step is, as long as our matrix is in the order, or system of equations are in the order where x, y's, and z's are all going to line up and the constant is on the other side, we're going to start by writing our augmented matrix. And so writing our augmented matrix here, I have 1, negative 3, 2, vertical line 6. Second row is negative 2, 1, negative 3, and then 10. And our third row is 1, negative 8, 3, and then 28. So again, we're working column to column. Working with our first column, we want a 1, and it's already where we want it in that first row, first column. So we're going to use this row 1 to manipulate and get zeros below it. And so let's rewrite our matrix with row 1 because we're not going to change it. We're just using it to change and manipulate the other equations. So 1, negative 3, 2, 6 for first row. And so you're thinking to yourself, what can I multiply 1 by and sum it to negative 2 and get 0? So my new row 2, I can get by looking at 2 times row 1 plus row 2. So 2 times 1 is 2, minus 2 is 0. 2 times negative 3 is negative 6. Negative 6 plus 1 is negative 5. 2 times 2 is 4. 4 minus 3 is 1. 2 times 6 is 12. 12 plus this 10 is 22. So now I want to move down to the third row and I want to make that 1 a 0. And so I can manipulate and change row 3 by looking at negative row 1 plus row 3. So negative 1 times 1 is negative 1 plus this 1 is 0. Negative 1 times negative 3 is 3. 3 minus 8 is 5. Our next row, next column, negative 1 times 2 is negative 2. Negative 2 plus 3 is 1. Negative 1 times 6 is negative 6. Negative 6 plus 28 is 22. I'm just checking to make sure that I did everything right. Okay, looking at my third row and this 5. If I did a -3 or -1 times this -3, that's +3. 3 minus 5, -8 is -5. So I noticed that my row 2 and my row 3 are the same. So technically, if I looked at negative row, if I make my row 3, new row 3, if I look at negative row 2 plus row 3, notice that I'm going to get a row of all zeros. Let me just write down row 1, 1, -3, 2, vertical line 6. Row 2, 0, -5, 1, 22. So my third row, I would have 0 plus 0 is 0. Negative of -5 is 5. 5 minus 5 is 0. -1 plus this 1 is 0. -22 plus 22 is 0. And so let's go back and let's rewrite out what this system of equations is with this matrix. And so if we rewrite this, this is x minus 3z plus 2, no, that's not 3z, minus 3y plus 2z is equal to 6. Our next equation is 0x minus 5y plus z equals 22. So our solution depends on what we choose x or y to be. So let's solve one of these equations for z. So for instance, let's solve this second equation here for z. So if we solve for z here, I would get z is equal to, add 5y to both sides, 5y plus 22. So let's go up into the second equation and let's replace z with what we found, 5y plus 22. And so doing that, we get x minus 3y plus 2 times z, which is 5y plus 22, is equal to 6. And so here we get x minus 3y plus, let's distribute our 2 inside the parentheses. So 2 times 5y gives us plus 10y. 2 times 22, so plus 44, is equal to 6. I can combine like terms, -3y plus 10y. So doing so, I get x, -3y plus 10y is 7y, plus 7y plus 44 equals 6. And so now in this case, let's solve for x. So notice that z is in terms of y. I want to rewrite x in terms of y. So let's solve for x here. So I want to get x by itself. So I can do so by subtracting 7y on both sides. So x is equal to -7y, and subtracting 44 on both sides. So 6 minus 44 is -38. So I get x is equal to -7y minus 38. And so our solution is a dependent system. It has an infinite number of solutions. Our solution, our x value is -7y minus 38. We have our y value. And we have our z value, and z is 5y plus 22. So in this case, and how we wrote it, our solution depends on what you choose y to be. So if I gave you a system like this on an exam, I might ask you to give me at least one solution to the system. And so one solution, well, choose a value for y. How about y equals 0? So if we go back in here and we plug in 0 wherever we see a y, we get negative 7 times 0 is 0, minus 38 is negative 38. So negative 38 would be our x value, y is 0. To figure out what our z value is, go in here. So we get 5 times 0 is 0, plus that 22 gives me 22. So one solution to that system would be negative 38, 0, 22. And so that should satisfy all three of these equations if we plug in those values for x, y, and z. So we can get another solution by choosing a different number for y and solving for x and z. Okay, so now let's look at one more system, at least. So looking at another example, we have x plus y plus z equals 6. First equation. Second equation is 2x minus y minus z equals 3. And our third equation is x plus 2y plus 2z equals 0. So rewriting our matrix, we would have first row 1, 1, 1, vertical line 6. Second row is 2, negative 1, negative 1, 3. And our third row is 1, 2, 2, and 0. Working with our first column, we have our leading one where we want it. So we're going to use that leading one, use that row 1 to get zeros in the entries below. So I know I'm not going to change my row 1. I'm going to keep it the same 1, 1, 1, and 6. But to get my new row 2, I could look at, well, negative 2 times row 1 plus row 2 would get me a 0 where I wanted it. So negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times this 1 is negative 2, plus negative 1 is negative 3. Negative 2 times this 1 is negative 2, plus negative 1 is negative 3. Negative 2 times 6 is negative 12. Negative 12 plus 3 is negative 9. So now we want to get a 1. And I'll make this 1 a 0. And so I see that I can make that 1 in row 3 a 0 by changing row 3. And I can do that by negative row 1 plus row 3. So negative 1 times 1 is negative 1, plus 1 is 0. Negative 1 times 1 is negative 1, plus 2 is 1. Negative 1 times 1 is negative 1, plus 2 is 1. And negative 1 times 6 is negative 6, plus 0 is negative 6. So noticing this, and I finished column 1, I would look at my column 2. I would want a 1 where this negative 3 is. So there's 2 ways I can do that. I can either swap row 2 and row 3 because I have a 1 where I want it. Or another way to do that is I can multiply my row 2 by a negative 1/3. So divide each term by negative 3. I notice that those are all divisible by negative 3, so I wouldn't have to deal with a fraction there. So let's just do that. So I have 1, 1, 1, 6. So negative 1/3 times 0 is 0. Negative 1/3 times negative 3 is 1. Negative 1/3 times negative 3 is 1. And negative 1/3 times negative 9 is positive 3. So notice that the row below is almost identical to that second row. We have 0, 1, 1, -6 for row 3. So notice if we did negative row 2 plus row 3 to get my new row 3, let's just rewrite row 1 and row 2 the same. So 1, 1, 1, 6, 0, 1, 1, 3. And our new row 3, well, -1 times 0 is 0, plus 0 is 0. -1 times 1 is -1, plus 1 is 0. -1 times 1 is -1, plus 1 is 0. And -1 times 3 is -9. -9 plus -6 is -15. So here's an example where this third row says we have 0x plus 0y plus 0z equals -15. And so there's no way that I can figure out what x, y, and z are that would make that a true statement. So this is impossible. And so we can stop. There's no solution to that system. And so we would say that this is an inconsistent system. It has no solution. So we just saw how we could use matrices to help us solve these systems of equations. We saw instances of each case that you would see where you would get one solution, infinite number of solutions, or no solutions. And so using these matrices can be really beneficial when you're solving huge systems of equations where you have multiple equations and multiple variables. It's just an easier way to kind of organize and keep things organized and to solve. We'll see using systems of linear equations when we look at these partial fraction decompositions, where we're going to take a complicated fraction and we're going to rewrite it as a sum or difference of multiple fractions. So you'll get a chance to see this a little more in another video.